When we think of waves, we think of sound waves, we think of water waves, and I want to broaden that definition a little bit. So for us as physicists, really what it comes down to is a wave is some sort of change in any property of the system that actually travels through space. Um, One thing to keep in mind with waves is there's no particles that are actually transported with the wave. You know, when you're talking about sound waves or water waves or waves on a string, those particles are moving in place for the most part. They don't move along with the wave. But what the wave does do is transport energy and momentum. So just to kind of rephrase this definition of a wave as a mathematical equation, in one dimension, what we can do is write out that y is equal to some function which depends on x plus or minus v times t. So the argument is basically comes as a chunk x plus or minus v times t. Now this y is not necessarily a spatial dimension. It's whatever property we're talking about that is changing. So just a couple of terms. A traveling wave essentially is any wave where the velocity is not zero, and this is opposed to standing waves, which we'll come across a little bit later on. And then a wave pulse is essentially just a short burst or a short finite time change in the properties. So this would be an example of a pulse where the time is finite. Now we're actually going to focus a lot of our time on harmonic waves. And so when we use the term wave, typically we are referring to the harmonic wave or sinusoidal wave, where the property in question is essentially defined by a sine or a cosine. Now just to kind of go through some examples of waves, of course we have the water wave that we're used to. The property in question that is changed from equilibrium is the actual height of the water. And in this case, the graph kind of looks like a side view of the water heights. Wave on a string is another example. The property in this case that is changed is the position away from the equilibrium position of a straight line. And y then represents the displacement. And so our graph of y versus x essentially looks like a snapshot of the string. So these are two examples of waves where there's physical movement. Now the particles themselves are not moving along with the wave. The particles are moving perpendicular to these systems. Now in a sound wave, the property in question is either the density of gas molecules, or we can talk about the pressure of the gas molecules. So here's an example where the graph of a sinusoidal wave does not look like the physical situation. What we have down here is essentially a variation in the density of the particles, where when we graph our wave, this would be a low density region, high, low, and so on. And so we still represent that with a sinusoidal graph, but we're not talking about a spatial dimension. Another example of a wave is a spin wave. And in this case, the property that is changed is the magnetic field that are caused by individual particles. And so if you consider these arrows here to be the direction of the magnetic field caused by a particular particle, what happens in the magnetic wave is that the direction of the spin, or the direction of the magnetic field, actually varies as a function of position. Quantum mechanics, we have the quantum wave function. The property in question there is a probability amplitude, and y in that case is the square root of the probability. Again, this one does not have a physical representation the same way that a water wave or a string wave does. And then finally we get to the case of the electromagnetic wave, which is what we're really interested in. In the case of the electromagnetic wave, the thing that's waving is either the electric field or the magnetic field. And so y, whatever we use here, is our electric field strength or magnetic field strength. We'll be spending a lot of our time just focusing on the electric field. So just want to point out that it's really only in the case of the water waves and waves on a string that y is actually a spatial dimension. This is very crucial that you keep this in mind as we're going through this. when we're graphing electric field strength as a sinusoidal wave, we are not graphing something that is moving transversely. It's not something that's actually oscillating physically. It's the field strength that is actually oscillating.